In laboratories, research centers, and technology companies around the world, powerful computers are processing enormous volumes of data every second. Artificial intelligence models analyze images, generate text, and simulate complex systems. Behind many of these workloads sits a particular type of processor that quietly became one of the most important technologies in modern computing, the graphics processing unit, or GPU. And one company built an entire ecosystem around it, Nvidia. On the surface, Nvidia designs semiconductor chips used in computers and data centers. These chips originally gained popularity for rendering graphics in video games. GPUs could process many calculations simultaneously, allowing game engines to render detailed environments and smooth animations. But the architecture of these chips turned out to be useful for much more than graphics. Traditional computer processors handle tasks sequentially. They execute instructions one after another, which works well for many everyday applications. GPUs, however, contain thousands of smaller processing cores designed to perform many calculations in parallel. This structure makes them extremely efficient for workloads involving large data sets. Scientific computing, image processing, and machine learning all benefit from parallel processing. Researchers discovered that GPUs could dramatically accelerate certain types of calculations compared with traditional processors. Nvidia recognized this opportunity early. Instead of focusing only on hardware, the company began building software tools that allowed developers to harness GPU power more easily. One of the most important of these tools became a programming platform known as CUDA. CUDA allowed developers to write programs that run directly on GPUs. Before this platform existed, programming graphics processors for non-graphics workloads was extremely difficult. CUDA simplified the process, giving researchers and engineers a way to use GPU acceleration in fields such as physics simulations, video processing, and artificial intelligence. Over time, this software layer became a critical part of Nvidia's strategy. Hardware alone can be copied or improved by competitors. But when developers build entire applications on a software platform, switching becomes much harder. As more developers adopted CUDA, a growing ecosystem formed around Nvidia hardware. Universities use GPUs for scientific research. Startups use them to train machine learning models. Large technology companies deployed them inside massive data centers powering AI services. The rise of artificial intelligence accelerated this trend. Training modern AI models requires processing enormous data sets through neural networks containing billions of parameters. These workloads involve vast numbers of mathematical calculations performed repeatedly across large matrices of numbers. GPUs excel at exactly this type of work. As AI systems grew more complex, demand for GPU computing power increased dramatically. Data centers filled with racks of specialized hardware designed to accelerate machine learning tasks. Inside these facilities, thousands of GPUs operate together as clusters. High-speed networking connects processors across racks so that massive training jobs can run across many machines simultaneously. Cooling systems regulate temperatures while power infrastructure supports constant high-performance workloads. But Nvidia continued expanding its ecosystem beyond individual chips. The company introduced specialized software frameworks optimized for machine learning. These tools integrate with popular AI libraries used by developers across the industry. By supporting widely used frameworks, Nvidia ensured that its hardware remained compatible with emerging AI research and applications. The ecosystem also includes development tools, simulation environments, and optimized libraries that accelerate specific workloads. Together, these components form a layered platform. At the base sits the hardware architecture of the GPU. Above that sits CUDA and other programming frameworks. On top of those tools run applications built by developers across industries. This layered structure creates powerful network effects. The more developers build software optimized for Nvidia hardware, the more valuable the platform becomes. Hardware demand increases as applications rely on the ecosystem, and the expanding ecosystem attracts even more developers. Yet the semiconductor industry remains highly competitive. Other companies design processors for data centers and AI workloads. Some cloud providers develop specialized chips optimized for their own infrastructure. The technology landscape evolves quickly as computing demands increase. Even so, Nvidia's strategy of combining hardware innovation with a strong developer ecosystem created a durable advantage. From the outside, the company appears to be a chip manufacturer, but beneath that label lies a broader computing platform. Data centers powered by parallel processors, software frameworks connecting thousands of developers, and an ecosystem that transformed graphics hardware into the engine behind modern AI infrastructure. What began as technology for rendering video game graphics became the foundation of an entirely new computing era. And Nvidia built one of the most influential ecosystems at the center of it,